All right, so for this second part of our videos on power series, in this one we are going to basically go the opposite way. We're not going to start with the series form. We are going to start with the function form, and so in this way we can see a function and then write a power series that maybe is easier to evaluate than the original function. But that's the idea. So let's start with the geometric series. So the geometric series, as we know, we have the sum from n equals 0 to infinity of x to the n, which when we write out the terms, we have 1 plus x squared plus x cubed, and so on. And so we know that this converges for x, absolute value of x less than 1. And we also know from previous videos that the sum of this will be 1 over 1 minus x whenever this is true. So this tells us that since the sum of this series is 1 over 1 minus x, we could say 1 over 1 minus x equals 1 plus x squared plus x cubed, and so on. Okay, so now we're going to use this. We're going to use this basic fact to figure out what power series we can use to define other functions. So we'll start with a very basic one, which is 1 over 1 plus x. So this looks very similar. And in fact, we could rewrite this as 1 over 1 minus negative x. So obviously these are the same. And so now we are in this form, 1 over 1 minus something, in this case minus a negative x. So let's write this as 1 plus a negative x plus negative x squared plus negative x cubed plus on and on and on. And of course we can simplify this. This would be 1 minus x. This would be a plus x squared, since negative x squared is just x squared, minus x cubed, and so on. And so we can write this as the sum from n equals 0 to infinity of negative x to the n. And so this function is represented by the power series negative x to the n. So that's the idea. So we want to take these functions. We're going to use the geometric series that we already know, and we're going to figure out how to rewrite these in a way that looks like a geometric series, but is a little bit different and gives us a different sum in the end. So now let's try 1 over 3 minus x. So now this one still looks similar, but instead of the 1, we have the 3 here. So now we need to figure out how to get it in more in the form of 1 over 1 minus x. So how could we do that? We could divide this, or divide everything, by 3. So that would give us 1/3 over 1 minus x over 3. So these are the same. Just divide everything by 3, and this is what we get. Now, we need a 1 on top. So let's factor out we'll pull out the 1/3. So let's write this as 1/3 times 1 over 1 minus x over 3. Okay, so now it looks more like this, because we don't really care what this one is. We really just want a 1 here and a 1 here. So now we have that. And then we're subtracting off x minus 3. So now this should be the sum from n equals 0 to infinity. We can pull out the 1/3. That's just a constant. We can pull that outside. And then whatever is subtracted here is the term that we're going to be raising to the n and adding up all our terms. Okay, so there we go. And we could write this, we could put the 1/3 back in if you like. And so that would just add another 3 in here. So that would be a 3 to the n plus 1 on bottom. And we still have the x to the n on top. So either one of these work. They're the same. And this might be a better way to write it, just depends maybe. All right, so the interesting thing about infinite series is we can differentiate. We're not really going to do that here, but we can also integrate term by term. So if we have this infinite series, which would be c0 plus c1x plus c2x squared and so on, we can integrate each of these term by term. So we already learned back in Calculus 1 probably that when you integrate a polynomial, you're really just doing it term by term. Well, if you have infinitely many, you just do it infinitely many times. And so if we want to integrate the series from n equals 0 to infinity of c sub n x to the n dx, then this is just, so the constant is not changing really. The integral of x to the n would be x to the n plus 1 over n plus 1. And then, of course, we have our plus c. So if we want to integrate a series, we can do it. Not too difficult to do. So now let's use this and find a power series representation for x to the 8th times arctangent of x cubed. Now, if you just saw the answer to this, you would think, how in the world, where did that come from? Because it kind of comes out of nowhere, it seems like. But it does make sense if you follow what we've kind of talked about already. So this x to the 8th, we don't really need a power series for that, because if we wrote this, I mean, there's not an infinite series for this. This is just x to the 8th is just the 8th term of this series with a 1 as the coefficient. So let's just set aside the x to the 8th, and we'll bring it back in at the end. But let's consider arctangent of x. And before we do that, let's consider 1 over 1 plus x squared. So maybe this looks familiar. If we wrote this out as a power series, let's write it as 1 over 1 minus negative x squared. This would be 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th, and so on. Now, can we write this as a sum from 0 to infinity? Well, every term is changing signs. So that tells us that we're going to have a negative 1 to the n. The first term is positive, so that tells us it's n here. If the first term is negative, negative, positive, negative, positive. If it was opposite, then it'd be negative with the n plus 1. So negative 1 to the n, and you can check this. If n is 0, this would be negative 1 to the 0, which is positive. Negative 1 to the 1 would be negative. So our first term is positive, second term is negative, and so on. So we got this right. Now, what do we get after that? If we're basically raising x squared to the n. Right? So we have x squared, x to the 4th, x to the 6th. So this is the same as x to the 2n. So we'll write sum from n equals 0 to infinity, negative 1 to the n, x to the 2n. So this series is these terms, and the sum would be 1 over 1 plus x squared. So now, what happens when we integrate 1 over 1 plus x squared? And what happens when we integrate the sum from n equals 0 to infinity, negative 1 to the n, x to the 2n dx. So these two are equal. So let's just integrate both sides and see what happens. So the integral of 1 over 1 plus x squared dx is just arctangent of x. And when we integrate this, of course, we'll get the sum from 0 to infinity of negative 1 to the n, so that's not going to change, x to the 2n plus 1 over 2n plus 1 plus c. Now, c is actually going to be 0 in this case, since arctangent of 0, or inverse tangent of 0, is 0. So that gives us, and when we plug in 0 for x here, we get 0. So 0 equals 0 plus c, so c is also going to be 0. So here, we don't have x, or at least in our up here, we don't have x. We have x cubed. So now let's substitute in x cubed. So that'll give us the sum from 0 to infinity of -1 to the n x cubed to the 2n plus 1 over 2n plus 1 plus c. And we can simplify that. -1. So we're going to multiply 3 times 2n plus 1, and we'll get 6n plus 3 over 2n plus 1. And we actually don't need that. C was 0, remember. Okay, so now what did we start with? We started with x to the 8th times arctangent of x cubed. Well, x to the 8th, of course, is not an infinite power series. It's just x to the 8th. So we can just multiply both of these by x to the 8th. Because whatever x is just a constant. So we're multiplying everything in this series by, it should be 1 to the n, -1 to the n, x to the 8th, x to the 6n plus 3 over 2n plus 1. So that gives us the sum from n equals 0 to infinity, -1 to the n. So now 8 plus 6n plus 3 gives us x to the 6n plus 11 over 2n plus 1. And there is our power series. And so, and you can check this, I guess, if you have a calculator, you can plug in a value for x. This will give you, your calculator will give you an approximate answer to 10 digits, or however accurate your calculator is. And then you could plug in whatever value you picked for x and figure out what the sum is, add up the first 10 to 12 terms, and you get a good approximation for whatever this is. So at least we did this right, and we did this right, so that should work. All right, but that's the idea. So we always start with the geometric series, and then whatever function we have, we may need to integrate to get to an inverse trig function, or whatever the case may be. But we're always starting with that foundation of the geometric series and kind of manipulating it to end up with the power series that we need in the end. So if you have any questions, please let me know.